Okay, so welcome everybody again. I was asked to give two presentations, and the first one is more the general topic of human energy expenditure, so more basic science about energy metabolism in humans, and the second one will be more about my personal research, so more applications of in the same area, but more specifically aimed at research. So the first presentation is more general information about human energy expenditure, and maybe some of you already know some things and some of you may not know all the things I'm talking about. So if you have any questions, feel free to interrupt me during the presentations. I don't mind, so if you need more information, if I'm going too fast, just let me know. So this is a little bit the outline of the first lecture. Let's start with the general topic of energy balance, and then we'll focus on the energy expenditure part. And then at the end I will talk a little bit about a few studies, what happens to energy metabolism, energy expenditure when you manipulate the diet, for example, or if you start to exercise or you do both. If you create a change in your energy balance, what happens to energy expenditure? So we start off with the concept of energy balance, and to do that we go to physics, actually, not physiology, but we go to general physics and back to the 19th century, where we need the first law of thermodynamics, and that means the conservation of energy. And the first law of thermodynamics actually says that you can transform energy, so you can change it from one form to another form, but you can never create it or you can never destroy it. So energy is always maintained in a system one way or the other. It can never disappear. And it also means that if you have a certain system, the energy content of that system equals the amount of energy that you add to the system minus the amount of energy that you are losing to the environment. And this first law of thermodynamics from physics, obviously it also applies to human beings. And I guess everybody knows Catherine Zeta-Jones, which is in the picture here. If you apply that law to humans, first law of thermodynamics, it means that you will store all the energy that you take in minus the energy that you are expending. So everything you will eat or drink, you will have to spend it again or you will store it in your body. And if there's just a small disbalance between energy intake and energy expenditure, as long as there's a balance, your body mass will not change. If there's a slight change in the balance, this could happen to Catherine Zeta-Jones. And as you all know, this is a little bit of a problem in our current Western society. So, what is energy metabolism? I like to see the complete picture, and that means I look at energy intake because I'm also a nutritionist, but during the PhD I focused on energy expenditure, and then there's this the body, but also the body composition that is in between. So these two are more my areas of research for the moment, and I studied this when I was a student in Belgium. So that means energy intake, and as nutritionists you all know it, you've got the carbohydrates, you got the fat, you got the proteins, and actually you also store the same components in your body, and you know that fat is the main energy source for living, but also proteins are quite important, and glycogen. You can store a little bit of carbohydrates, not a lot, but you can store a little bit in the muscle and in the liver, and this becomes very important during exercise, of course. And then on the other side of the equation you have the energy output, and we'll talk about a little bit about the different components of energy expenditure, and I will also talk about what determines or what are the main determinants of human energy expenditure. And some of those are body size, body composition, age, gender. Maybe if we have time we'll talk a little bit about disease as well. So I like to see energy metabolism as, you know, the big picture, what goes in, what is stored, and what goes out. Now let's focus on the expenditure part. What do we need energy for as human beings? First component is what we call the basal metabolic rate. That means when you are lying on a bed at rest and you are fasted, so you measure it in the morning, you will need quite a lot of energy just to breathe and keep your heart pumping and to maintain the temperature of your body, and so on and so on. So this is a major component of all the energy that you spend during a day. The diet-induced thermogenesis is not such a big component, but it does mean that everything you eat, everything you drink, part of the energy in that food will be used just for digestion, absorption, and storage of that food. So part of the energy is basically lost immediately. And then physical activity, of course, it's a very variable component. Some people are not very active, others are really active. So it depends. The size of this component depends on how active you are during a day. There's, of course, sports, and there are non-sports activities, things you have to do every day. Generally, these non-sports activities are the important ones, because you don't do that much of exercise in a week, for example. So if you talk about energy expenditure, these non-sport activities are the main components where you actually need your energy for. Now, to put it in perspective, I think it always helps to, if you compare human beings to, for example, a vacuum cleaner or to a desktop computer, then these devices need a certain amount of energy. Like a vacuum cleaner is 1800 watts, which is quite a lot because it can't do that much. It can just clean the floor. And a desktop computer needs 200 watts. So my question is, where do you think human beings are situated in energy expenditure if you compare it to these devices, for example? How many watts do we need during a day? Does anybody know? Does anybody dare to take a guess?
More than 1800.
More than the vacuum cleaner, you think? Yeah? Anybody else wants to challenge that guess? Who thinks it's more than the vacuum cleaner? We've got 2. So who thinks it's less? We've got 1. So what does the rest think? You stopped thinking a while ago. Okay, then I'll just tell you. It's 150 watts for human beings. So that means 3 light bulbs, well, old light bulbs, we've got LED lights now, but you are all 3 light bulbs. And that's how much energy you need, or how little energy you need to do all the things you do during daily life. Yeah? And this is actually for quite a big man, 150 watts. A smaller woman will only have 100 watts, for example. But just to put it in perspective, we are very efficient creatures. So the components, if you look at the different components of the energy expenditure, this is sleeping metabolic rate. So during the night, when you go to bed, it will start slowly to decrease your energy expenditure, and usually around between 3 and 6 in the morning you reach your sleeping metabolic rate. So you're really the lowest metabolic rate that your body will reach during a day. If you are just awake, what we call arousal, you will add about 5%, 5 to 10% even, to sleeping metabolic rate, and then we talk about the basal metabolic rate. This basal metabolic rate in an average human being, it's about 60 to 70% of all the energy that you need. So everything you eat and drink, about 60 to 70% is just maintaining the body. About 10% is diet-induced thermogenesis. So if you eat something, 10% will be used for digesting and storing the ingredients or the nutrients. And then we have the physical activity related energy expenditure, and that is of course the most variable. Depending on how active you are, in general it's about 30% on average in human beings, but it can be 50% or more. If you are an athlete, it will be a lot more. So these are the different components put into perspective, and then the exercise thermogenesis here and you have the non-exercise thermogenesis. And this has been topic of some debate, where this is the most important part of exercise or physical activity thermogenesis, whereas exercise is usually quite limited during a week. Okay. Now the question is, how can you measure all these components? And I'm going to go back in history first to the 16th century, because this guy came up with some way to measure his metabolic rate, at least get some idea of it. Does anybody know what is represented here? You know him? So what is he doing? Everything out, yeah? Yes, exactly. So he's sitting on a scale here. This is attached to a scale. So he's weighing himself, but he's also weighing everything he's eating, and he's weighing everything, as you say, coming out again. And at some point, because he was sitting there for quite a while, I mean, you have to admire him for doing that, just sitting on a chair for a day or a few days. But he noticed something was missing. So weight was disappearing, and he didn't know where it was going to. And so he had no idea how to measure his metabolic rate, but he did notice that something disappeared that had a little bit of weight. And he termed it the insensible perspiration. But we now know, of course, that he was losing weight by breathing. So he was exhaling CO2, and the CO2 was causing him the weight loss. But this goes back 4 centuries. And if we go back about, let's say 2 centuries, then we had Lavoisier with a direct calorimeter. And this is maybe also a familiar picture, where he put I think it's a guinea pig. He puts it in a bucket of ice, basically, and the ice is surrounded by ice water to insulate the cage from the environment. So you had an insulation in temperature from the outside environment and the inside. And what he was doing is just measuring the amount of ice that melted, caused by the little animal inside this cage. And as you know, if you know how much calories you need to melt 1 kilogram of ice, for example, he could calculate the amount of calories that this animal was using during a day. This seems like a technique that is not very comfortable or applicable in human beings. So over time we did come up, well, not me, but other researchers came up with other devices to try to measure the metabolic rate. But first, if you have a fire burning, basically that means that you have the nutrient, or in this case it's methane, it's not wood, but anyway, it's methane, you need oxygen to burn it, and CO2 will be produced. So that's like a fire burning. And human beings are almost the same. The nutrients are different, of course, so this is glucose, for example, but we also need the oxygen to burn it, and we will also produce the CO2 to release energy. Can be heat, can be ATP stored in the body to use for physical activity, for example. So humans are like a fire, but a little bit more controlled. So measuring it means you can do it directly or you can do it indirectly. Directly is measuring the heat, like the guinea pig inside the cage, where you see how much ice is melting. And you can do it indirectly by just measuring, the oxygen that is being consumed and the CO2 that is being produced by the human body. The direct one is used to be applied quite a lot in the past, but it's technically very difficult to measure it, but this is, for example, a whole room direct calorimeter, where you have your person inside, and actually the heat loss of the person is being measured by having water flowing through the chamber, and you measure the temperature of the water at the inside, and you measure the temperature of the water at the outside, and the change is the heat that has been produced by this human being. This is actually a combination of a direct and an indirect one. This was also an attempt to get an indirect calorimeter. But the concept of direct calorimetry usually is having a water inlet and a water outlet and measuring the temperature change when your subject is inside. And this is very hard to use, so it's hardly being used anymore. It's still used in Canada, for example, but in Masstricht we don't have a direct calorimeter. We do have this direct calorimeter, which is a suit calorimeter, and the principle is the same. But you just have to wear this suit where all the water tubes are inside the suit, and you're again measuring the temperature here and the temperature there, and the change is the heat that has been produced by your subject. But it's a little bit difficult to wear. You know, this is an example. If you got to wear this suit the whole day, it's not really comfortable. Certainly not here in San Sebastian, when it's a little bit warm outside. So you can still apply this, you know, in a laboratory setting if you have some specific interest in direct calorimetry. But you can imagine this is not a method to measure energy expenditure of human beings on a large scale. So we like to rely on indirect ways to do it. And where does the indirect calorimetry comes from? We know how much liters of oxygen we need when you are burning 1 gram of carbohydrates. We also know how much CO2 is being produced if you're burning that same gram of carbohydrates. And we also know how much energy is released from that certain substrate. We also know it for proteins, and we also know it for fat. And you can see for fat, for example, to burn 1 gram you'll need a lot more oxygen. Actually a lot less CO2 will be produced. And the energy released from fat is the highest. So this would be like 9 calories per gram, and these are 4 calories per gram. So fat has the highest energy content. If you look at it in energy per liters of oxygen consumed, then carbohydrate is the most efficient fuel for the human body. Yeah, so carbohydrate will give you the most energy for 1 liter of oxygen that you are using. And fat is a little bit less efficient, and protein is even more or even less efficient than the other two. But these numbers, with these numbers you can make the equation that is below here, where you actually have the amount of oxygen consumed. If you measure that, you measure the amount of CO2 that is being produced by the body, and you measure the amount of nitrogen in the urine as a way of protein oxidation, then you can calculate energy expenditure of a human being. So you need to measure 3 things: oxygen, CO2, and nitrogen. Usually we only measure 2. In general, we only measure the oxygen and the CO2, and we neglect the urinary nitrogen. It doesn't mean that protein oxidation is not important. It just means that if you have about 15% of protein oxidation a day, because you eat about 15% of protein in the diet, then the equation will be correct if you just use oxygen and CO2. And if you are eating a little bit more protein or a bit less, the error that you are making in calculating energy expenditure is very, very small. Yeah? Unless you really want to know protein oxidation. But if you're not interested in protein oxidation, you can just measure oxygen and CO2 and you will get the right answer. So these are the numbers where indirect calorimetry is coming from. These are some techniques. Are you familiar with the ventilated hood? Is anyone familiar with the techniques? Yeah? Okay. So this is a picture in one of our laboratories, quite an old picture actually. You have the air inlet here, so we just there's an airflow from the room through the hood to the system, to the indirect calorimeter. So what you have to measure is At the inlet, you have to measure oxygen and CO2 concentration in the air, and at the outlet, you also have to measure oxygen and CO2. And the difference is, of course, what this human being here has been using and producing. And we call that the ventilated hood technique, and we use this to measure the basal metabolic rate. You could also use it to measure diet-induced thermogenesis, but then you would have to measure for like 6 hours after a meal, for example. So it's more difficult to lie still under a hood for 6 hours. But this is one example of indirect calorimetry. Second one we use quite a lot is during exercise, knowing what the energy expenditure is during exercise, and then instead of this hood you have a mouthpiece or a little mask. And the advantage of the mask is that you have a much quicker, a higher resolution. You will see the results on the computer a lot faster than with a ventilated hood. So within 20-30 seconds you will see the result of the energy expenditure appearing on your computer. So during exercise you apply this technique, or you measure physical fitness, VO2 max, see what the maximal oxygen uptake of human beings is. Then you apply a face mask. And if you want to see the bigger picture of human energy expenditure, we use a whole room. So we use a whole room indirect calorimeter, which means that we lock our subjects up for a day or 2 days, or worst case scenario 7 days maybe. And the whole room is your indirect calorimeter. And we now have 5 of these in Masstricht. So basically you do have a toilet, of course, and you got a television, and you got a computer with internet, and a bed and a sink here. We had a very nice view at the mortuary also, so you have a look outside, a view outside. And what you actually measure is the total energy expenditure of the subject inside for 24 hours or 36 hours or longer than that. You can see sleeping metabolic rate during the night. You can calculate diet-induced thermogenesis, and you can see some of the physical activity-induced energy expenditure. But you can imagine in a small room like this, this component is going to be relatively small. So it's still no way to measure physical activity-related energy expenditure in daily life. It just gives you an idea, but this is not a daily life situation. And usually we are interested in a daily life situation. So if you want to measure energy intake or food intake, you want to know what somebody is eating during daily life. And so we also want to know what they are using during daily life, and that's when we use so-called doubly labeled water technique. And the advantage here is that you don't have to lock up your subjects inside a room. You can just let them go, do whatever they want to do for 2 weeks, for example, and we get a very accurate measure of their total energy expenditure during the 2 weeks in their daily life situation. Now, how do you do that? We use stable isotopes. The stable isotopes oxygen 18 and deuterium. So in this bottle of water we have water containing normal water, but also water containing both isotopes here. And the oxygen 18 will leave the body again as CO2, but also as water, as H2O. Deuterium will only be leaving your body as water. Yeah? So actually the difference between those two elimination rates from the body will give you a measure of the CO2.
May I ask you about the differences between indirect method, you show us, and hot water technique? This capsule with the human body.
Yeah.
Right?
Well,
what's your opinion about hot water? Because this is northern one, and some favorite sports clubs both this technique use.
Yeah. Well, hot pot is actually a technique to measure body composition and not energy expenditure. I will get back to that. I can get back to your question in the next presentation, because I will be talking about body composition a little bit. But it doesn't give you energy expenditure. It gives you the body composition. Yeah. So I will get back to it later. This technique, so this is the only technique you can actually use in daily life, and it's a highly accurate technique. So, but what you're measuring here is just the CO2 over 2 weeks, for example. So what you do is you collect a baseline urine sample, and you measure the isotopes that are present in the human body, because everybody has these isotopes inside this water pool. Then you provide them a little bottle of water containing these 2 isotopes, and then the only thing your subjects have to do is collect urine samples on day 1, day 8, and day 15. And that's all. So you don't have to keep them in a laboratory, and you will get energy expenditure over a longer period of time in daily life. Okay, so this is the last indirect method that I wanted to say something about. There is a bit of a difference between direct and indirect calorimetry. And this is an old publication from Paul Webb, who was quite an important person at the energy metabolism field. And what you can see here, because on the left here is metabolic rate. Total metabolic rate, what I've indicated here. So this bar is total metabolic rate of your subject. And this is the heat loss of your subject, so measured directly. And at rest, you can see that the 2 techniques will give you the exact same answer. So when you are at rest, all the energy that you are using is being lost as heat. When you start walking or cycling, you see that there is a gap appearing here between direct and indirect calorimetry. Because at this point, when you are walking, some of the energy is being used for the physical activity, and it's not being released as heat anymore. Yeah? So that means indirect calorimetry will give you the right answer during physical activity, for example, but direct will miss this component of the energy that I'm putting in the actual movement that I'm doing now. So now I'm losing some energy to probably friction with the floor or friction with the air or whatever, but you wouldn't measure it with a direct calorimeter, because it's not being lost as heat. Okay, so that means if you want to measure energy expenditure, that means that we prefer, in these days, the indirect method. You have to measure these oxygen, CO2, and nitrogen, but usually you can just do these 2, oxygen and CO2. And during exercise, there will be a difference between the direct and the indirect technique. Okay, so that were the components and how to measure it. And we can say a little bit about the determinants now of human energy expenditure. So is there a difference between men and women, or is there a difference between this guy and the other guy, or these 2, if you remember these, or the 2 at the bottom? So size may be important, gender may be important, how active you are. So let's have a look at the main determinants of how much energy you need during a day. And the most important one, it's probably not a surprise, I think you all know, is the body mass. So here is sleeping metabolic rate measured, and here's body mass, and then you see this very strong correlation between the body size of a subject and how much energy he needs at rest. So about 72% here of your energy expenditure is explained by your body mass. So just knowing body mass of a subject, you can already have quite a good estimate of how much energy or nutrition he would need during a day, he or she. There is of course a difference between men and women, and the difference is in the body composition, because women have a higher fat percentage than men, and that means that men have higher fat-free mass, and the fat-free mass actually is the most important determinant of your energy expenditure during the day. The higher your fat-free mass, the higher your energy expenditure. And you see the correlation here between fat-free mass and again sleeping metabolic rate. And now you can explain about 78% of his energy requirements. So if you know somebody's fat-free mass, you can quite well predict how much energy he will be needing during the day. Women are here, at the lower part of the line, and men are up there. But you can see that both men and women are exactly on the same regression line. So if you take fat-free mass into account, men and women are quite the same as it comes to energy expenditure. So the gender difference is generated by the body composition. What you should not do is express sleeping metabolic rate divided by fat-free mass, because then, as you can see here, if you do that, you will get a higher metabolic rate for women compared to a lower metabolic rate for men. And this was a significant difference. What you've done here is made a statistical error by dividing y by x and neglecting the intercept here. So men and women are exactly the same if you correct for fat-free mass, but you shouldn't just divide, because then you're neglecting the intercept of the regression line. Is that a little bit clear? Yeah? Okay. So, body composition. That means fat-free mass is the best predictor, and men or women are the same if you properly correct for that difference in body composition. This was just for sleeping or basal metabolic rate. What determines your diet-induced thermogenesis? On average, it's about 10%, but there are some differences between the different nutrients. Carbohydrate has a diet-induced thermogenesis of 5 to 10%, and fat is very low, 0 to 3%. So we're very efficient in storing and digesting our fat, unfortunately for some people. And protein is a very inefficient nutrient, so you lose about 20 to 30% of the energy in proteins you lose for digestion and storage. And then on average, if you combine all these, on average you will get 10% of total energy expenditure used for digestion and absorption. So, if you look at total energy expenditure, again, body mass is the main predictor. So all the components together, again here body mass on the x-axis, is the main predictor of total energy expenditure. And there's a bit of a difference between men and women, as you can see, and that's of course the body composition again. And there's a lot more variability around the line, of course, because that is physical activity that is not taken into account. But it does mean a very simple thing, which is unfortunate for people who are trying to lose weight. If you are losing weight, you will slide down the regression line, and of course you will decrease your energy expenditure. Meaning that if you go on a diet, you will have to maintain this lower energy intake for the rest of your life, or you will slide back up. And that's what they call the weight cycling, or the problems with keeping the weight that you have lost, keeping your weight loss. So you will have to maintain your diet for the rest of your life, which is a bit hard to do, apparently. Okay, so let's talk about physical activity then. It's usually, or it can be expressed as energy expenditure. What you do then is you take 90% of total energy expenditure and you subtract the basal, and then you have your activity-related energy expenditure. And another very common way to express it is physical activity level. So you divide total by basal. Yeah? So if you are at rest, your physical activity level will be 1. And if you're starting to move around, on general, during a day, on average, we have about 1.7. 1.7 is the average physical activity level of human beings. And then you can also measure, maybe not the energy expenditure, but you can measure just the body movement. And we do that with accelerometers. So we want to know how much you are actually moving during the day. And this is one device, but there are many more on the market. Are you familiar with accelerometers? Pedometers, like little step counters, you know this? This is a more advanced step counter basically. It's an electronic device, and it also measures every acceleration in 3 directions. Yeah? So both horizontal planes and also the vertical plane. So we wear it at the lower back, so every movement we're making is being registered as an acceleration. And the advantage of using such a device is that it gives you a total amount of physical activity over a week or over 2 weeks, as long as you want to wear the device. But it also gives you some more information about the physical activity pattern, because it's telling me when somebody has been moving, how intense the movement has been, for how long he has been moving. So you get a little bit more information than by just using doubly labeled water, for example. And these devices are very small and very lightweight, so they don't really bother you when you're wearing them. So this is a very nice technique to capture physical activity, and this is just one example of what it looks like. 24 hours here and there as well. Well, not even 24, till 1 o'clock at night. So you look at the pattern from waking up until going to bed. And this is a subject who is involved in cleaning activities at the university. And this is a subject who is doing desk work, like me, for example. So you can see a huge difference in physical activity during the day, just depending on the job that you have actually. So this is what it looks like. For every minute you get a value, so you can see exactly when somebody is moving and how much somebody has been moving around. And there are many devices on the market that you can buy. This is one we use, but I also use the Actigraph now, and you have the Caltrack RT3 and so on and so on. So there's a lot of devices on the market that you can use to measure your physical activity in daily life. If you have a decent accelerometer, the advantage is that you can at least get some idea about total energy expenditure of your subjects as well. And this is a validation that I did with this accelerometer, and I used doubly labeled water to assess the energy expenditure during daily life. And you get this very nice correlation here, where with my accelerometer, and then I add age and body mass and height, with those variables I can predict my total energy expenditure up to 1 megajoule accurate, individual error. So there's the R value, but the standard error of estimate is 1 megajoule on the individual level. So on the group level you would be right, on the individual level you could be up to 1 megajoule off. But this is it's a cheaper device and easier to use device, and you will get a nice measure of total energy expenditure in daily life. If you have a proper accelerometer, of course. Okay, so what happens if you try to change your energy balance by going on a diet, for example? And there are no questions so far? Okay. So let's go on a diet. And well, it's quite simple, this slide, I think. If you take 90% of your normal energy intake, you will lose some weight over a few weeks. And if you take 70%, you will lose weight quicker. I mean, that's not a surprise, that's how it works. So if you just restrict the energy intake part, you will lose weight over time. And this is the unfortunate event, the unfortunate consequence of losing that weight, because these are the three components of your energy expenditure: basal, diet-induced, and physical activity related. And by losing weight, all these three components significantly decrease, resulting in a major gap in or decrease in your energy expenditure rate. So you go on a diet, and you will have to, after the diet, you will have to maintain this level of energy intake, where you were used to this level of energy intake, to maintain your balance. So diets don't work unless you maintain them for life. And that's a problem. And then many people have thought, well, you can go on a diet, you restrict energy intake, but what if I also increase my exercise or my physical activity? So you work on both sides of the equation, decrease one and increase the other. If you go on a diet alone, it's a bit of an older study, but this is a review of 46 studies actually, so I'm still using it in my presentation. That if you go on a diet only, that's what this stands for, you will lose some fat-free mass, and you will lose a lot of fat mass in women and in men. And this is the unfortunate part, that you're also losing fat-free mass. Always when you go on a diet, it's never just fat mass, it's always also fat-free mass. And that's a shame, because the fat-free mass is, your determinant of energy expenditure. And this drop is the main reason why energy expenditure goes down. If you go and add exercise to the diet, this is diet plus exercise, then you'll see that the weight loss, total weight loss, is not more than when you were just going on the diet alone. So the fat loss here is the same. Here it's even a little bit less. And the fat-free mass, the loss of fat-free mass, is less than when you were just on a diet. So exercise, it does help to preserve your fat-free mass while being on a diet. But if you make the sum of this, then you will actually lose less body mass than when you are just going on a diet. So it could be very disappointing for people if you're standing on the scale and you're seeing that you're losing actually less weight when you're adding exercise to your diet. But there's this shift in body composition. And this is of course a good thing. Losing less fat-free mass, that's a good thing. But it won't make you lose more body mass. So energy expenditure of course will decrease. Exercise training does not seem to result in further weight loss, but it is very helpful to maintain fat-free mass, and it's also helpful to maintain the weight that you have already lost. That's the good thing about exercise. Exercise alone is difficult, as a weight loss strategy at least. This was a study of Klaas Westerterp, who I've been working with for about 12 years now. And they decided to have subjects training for a half marathon. And the BMI ranged from 19 to 26 of the subjects. And the training was here 26 weeks. So this is the BMI. I think the training was for half a year or a year. And what they noticed is from a BMI of 23, 24, it became very difficult to participate in the training program. So they showed dropout only at the higher BMI range. And at the lower BMI range, there was no dropout of the program. So having a higher BMI itself is already a problem to start exercising. And then the question is it efficient to lose weight, exercise? And these are 3 different studies. One was the jogging study that the previous slide, so it was 40 weeks of training. This is a weight training program, and there's a cycling training program. And this is the physical activity level. So what I said, 1.7 is about the average physical activity level in humans. And they all increase to a huge extent in their physical activity level. So 2.1, that is quite a lot. I can guarantee you have to move around quite a lot to achieve this physical activity level, or a 2.04. But the body mass, in none of these studies it really changed. Here they lost 1 kilogram. So you go 40 weeks of jogging, 40 weeks of exercise training, intense exercise training. You get to a really high physical activity level and you lose 1 kilogram. So this could be a little bit disappointing if weight loss is the aim of your exercise. Of course you will become more fit and more healthy, but weight loss is not the way. This is not the way to achieve weight loss. And that can be very disappointing. So there's 2 reasons. One reason could be that you become more efficient. The human body becomes more efficient with the energy expenditure. Or you just start to eat more to keep up with the higher energy expenditure level, with the high physical activity level. The same study, the 40 weeks running, they did show a loss of fat percentage, especially in the men. So depending on how much fat you had to start with. So if you have this guy had a fat percentage above 30, when he started the training, he also almost lost 8 kilograms of fat. This one only had maybe 17 or 18% and could hardly lose any fat. So there was a relationship between the amount of fat that you had initially and the amount of fat that you were losing caused by the training. And in women there was no relationship. Maybe unfortunately, but apparently women, they tend to defend their fat mass to a higher extent than the men do. So training, problem with training is first of all if you already have a slightly higher BMI, the training load will be difficult. Second thing is it does not seem to result in weight loss, and you will actually gain or lose less fat-free mass. So the change in body mass will be more limited. Okay, so these are the main things. I can show a few more slides on what happens during disease, if you like, or I can leave it at this. Disease? You want disease? Okay. One study about rheumatoid arthritis, because this is one of my own interests. I'm measuring people with rheumatic inflammatory disorders, and I'm measuring their body composition and their energy expenditure. And if you have rheumatoid arthritis, these people were measured, their energy expenditure was measured. So black bars are the patients, these bars are the controls. And at rest, these subjects already had a 12% increase in their energy expenditure caused by the disease. And if they start walking on a treadmill here, and the speed of the treadmill is increased, and here the slope of the treadmill is also increased. Oh, sorry, this is the speed. Anyway, increasing intensity of exercise, then you see that here up to 19% higher energy expenditure in patients. So the disease itself is causing quite a big increase in the energy requirement of these subjects.
What is the reason? What is the reason?
The reason at rest, the reason seems to be inflammation.
Yeah.
So if they have an active period of inflammation, they will show an increased energy expenditure. When they are in a stable phase, because they have flare-ups and it goes up and down the disease state, if they are in a stable state, then you won't measure this difference at rest. The difference during exercise could be inflammation, could also be a different way of moving because they have joint problems, of course. It could be all kinds of reasons, but the research in this area is quite limited. And there's not a lot of studies showing these things. But you can imagine if it goes up maybe during a day about 15%, that's quite an increase in your requirements. Just one more study about patients with chronic obstructive pulmonary disease. And this is this disease is causing inflammation, but this is a disease that has a major impact on the life of these patients. And if you just look at patients versus control, just the weight, so on average they are much, much lower in body weight. But you can also see here fat-free mass. This is the fat-free mass index, so you divide fat-free mass by weight squared, by height squared, just like you do with the BMI. They are a lot lower, so they actually are cachectic, so they are losing a lot of muscle mass. And if you look at their fat-free mass adjusted resting energy expenditure, then you see that they are a lot higher than the controls. So the disease itself, being at rest, causes a major increase in their energy requirements. Now, they asked these subjects to just do this simple exercise where they had to stretch their arms and lift their arms while sitting on a chair. That's all they had to do. Just stretch the arms and lift the arms. And it caused an increase in their energy expenditure. In healthy subjects, about 5%, but in these patients, 12 to 14%. So just lifting their arms, they just needed twice as much energy as healthy subjects would need. And this is a very modest physical activity, of course. You can imagine that these people have to function in daily life, that their energy requirements will go up tremendously. And that's, of course, one of the reasons why you see this massive weight loss here, and also this loss of fat-free mass and the low BMI in these patients. And it's also shown in the heart rate, because just lifting their arms would lift their heart rate up to 105, for example, beats per minute, where we would be between 65 and 70 somewhere. So it has a major impact on their energy expenditure. Now for this presentation I want to stop here. So if you have any more questions about all this, we can maybe have a brief discussion now.